Hello everyone, let's start a new question. Discuss various forces acting on a gravity dam with a net sketch. Forces acting on gravity dam. The various forces acting on gravity dams are as follows: water pressures, wave pressure, weight of the dam, sill pressure, and uplift pressure, wind pressure, ice pressure, and earthquake pressure. So those eight pressures are acting on a gravity dam or any kind of dam. Now, first is the water pressure. Water pressure P. Let's consider P as a water pressure is the major external forces exerted by water stored in reservoir on upstream phase of the dam. If we create a dam, sorry, if we create a dam, so the pressure that created by stored water, it is called as a water pressure. This is a total pressure is P. It is calculated by the law of hydrostatic pressure. We have studied these things, hydrostatic pressure, on fluid mechanics subject during semester 4 distribution, which is a triangular as shown in a figure 5.470. So P here is the formula. P is equal to 1 half YW into H square. So first, when upstream phase is vertical, there are conditions when upstream phase is vertical, when upstream phase is partially vertical and partially inclined. This kind of case also given. When upstream phase is vertical, when the upstream phase is vertical, the intensity of the pressure is zero at the water surface and the equal to YW into H at the base. So YW is just a unit weight of water, and H is a height or depth of the water, or depth of the water. So intensity of the pressure at base, if we want to calculate the what is intensity, so we have the pressure is equal to YW into H. YW value of the YW is 9.81 kilonewton per meter cube or 100,000 kgf per meter cube. Total water pressure P per unit length of the dam is equal to the area of pressure triangle. So P is equal to 1 by 2 into YW into H into H. We can also say H square. Where it act at H by 3 of the base. These pressure acted on H by 3 from the base. When upstream faces is partially vertical and partially inclined. When upstream faces is partially vertical and partially inclined, the resulting water forces can be resolved in two components. First is horizontal component and second is a vertical component. Vertical component P is equal to weight of the water stored in a column A, B, C, and A, B, C, and A act and center of gravity of the area. So it will be act at center of gravity of the area. Now horizontal component for pH, P horizontal pressure at horizontal is equal to 1 by 2 into W into H square, which is acting at H by 3 of the base. Tailwater pressure. If there is a tailwater of height H dash on a downstream side, it will have vertical and horizontal components as shown in a figure. Horizontal component PH horizontal is equal to 1 by 2 W YW into H square acting on H by 3. Vertical is equal to weight of the water containing by column EFG. There is a column EFG, it's contain tail water EFG. So this component carry the vertical pressure. Weight of the dam. Second is the weight of the dam. The weight of the dam per unit length is given by a product of area of cross sections of the dam and the specific weight of the construction material. Example like concrete, and it acts act as a vertically downward at the center of gravity of the section. For the sake of the convenience, the entire cross section of the dam may be divided into smaller sections of the simple geometric shapes such as triangular, rectangular, etc. At the weight of each of these acting at its center of gravity may be considered weight of any part of the dam cross sections area of that part into specific weight of the material. So W into A into Y. For concrete, Y is equal to 24 kilonewton per meter cube. Third is the uplift pressure. Uplift pressure is defined as the force exerted by water penetrating through the pores and cracks and fissures within the body of the dam. the contact between the dam and its foundations, and within the foundation it acts vertically downward, vertically upward at any horizontal section of the dam as well as in foundations, and hence it causes a reductions in effective weight of the portion of the structure lying above the section. There are over the area over which the apply pressure acts has been a question for investigation. These are two schools of thought existing in the literature. One school of thought recommends that value 1 by third or 2 third as effective area over which the uplift acts. So one study says that there is a value where the pressure acts at 1/3 or 2/3 of effective area. As per other studies which will done in Terzaghi and uh, Lilievsky, sorry for the name, the effective area may be taken equal to the total area. So effective area will be total equal to total area. Terzaghi says that total area effective, it's a total area that acting uplift acts. The present practice in the design is to follow USBR, American Standard Bureau of Reclamations, which considers the total area as the effective area of a count. So if there is a total area A and the uplift pressure is, if we consider something that U, consider U as the uplift pressure. So total area is equal to effective area of the uplift pressure. Okay, USBR recommendations. As per USBR recommendations, the uplift pressure intensities at the heel and the toe should be taken equal to their respective hydrostatic pressure and joints by the straight line shown in a below, where no drainage gallery provided. Uplift pressure at heel is equal to gamma W into H, and uplift pressure at toe for heel it's gamma W into H, for toe it's gamma W into H dash. Okay, when uplift pressure gallery provided, uplift pressure at heel gamma W into H, uplift pressure at toe gamma W into H dash. Uplift pressure at gallery, if there is provided any gallery, drainage gallery here up here, so a YW into H dash plus Y 1 by 3 into H minus H dash. So this is the formula. This is for toe, this is for heel, and this is for toe. Here the all the diagram, uplift pressure diagram has been shown for no drainage gallery. If there is a drainage gallery provided just like this, so there will be change in uplift pressure also. Okay, fourth is the ice pressure. Ice pressure is exerted on a dam by a sheet of ice formed on entire water surface of the reservoir when it is subjected to expansion and contractions with changes in temperature. The coefficient of thermal expansion of ice being 5 times more than the concrete, the dam face has to be resist the force due to the expansion of ice. These forces acts linearly along the length of the dam at the reservoir level. As per the Indian standard 6512 1984, ice pressure may be taken equal to 250 kilonewton per meter square applied to the face of the dam or anticipated area of contact of ice with the face of the dam. Fifth is a wave pressure. If there is water, there will be also a wave pressure. Wind blowing over the water surface in the reservoir exerts a drag on a surface due to the which ripples and waves are formed. The impact of these waves produce a pressure on the upper portion of the dam. The magnitude of wave pressure mainly depend on the dimension and waves which is turned depending on extent of water surface and the winds. Earlier, as recommended, IS 6512 1972 for determining the wave heights, Molitor's formula was used. Formula is that HW is equal to 0.0322 under root VF plus 0.763 minus 0.271 under root f is equal to f is less than, if there is f is less than 32 kilometer. F is the fetch or straight length of the water in kilometer. V is the velocity of the wind velocity, and SW is equal to height of the wave in meters. SW is equal to 0.0322 under root VF, where F is equal to greater than 32, means the straight length of the water is more than 32 kilometer. Then this formula will be used. The pressure intensity due to the wave is Pw is equal to 2.4 Yw into Hw, or lambda W into Hw, acting at 1/8 of Hw meter above the stream water surface, still water surface. The pressure distribution in curvilinear, however, for design it is assumed to be represented by a triangle of height equal to 1/5 of HW. The total pressure is given by PW is equal to area of the triangle, 2.4 into YW into HW into 1 half into 5 by 3 into HW. So we will get 2 YW HW square. This pressure acts as a 3/8 of HW above the reservoir surface. Now 6 is a sill pressure. Practically all streams carries the seals along the water, which during the flood may be enormous quality. The seal load gets deposited to appreciable extents when the dam is constructed. The dam is therefore subjected to seal pressure in addition to water pressure. For determining the seal pressure, we have the Rankine formula. We have studied the Rankine formula so many times. PS is equal to 1 by 2 into gamma dash into h square in bracket 1 minus sin theta by 1 plus sin theta, acting at h by 3 height of the dam. PS is equal to total silt pressure, while gamma W is equal to submerged unit weight of the silt, and H is equal to depth of the silt deposit, and phi is equal to angle of internal frictions of silt. Seventh is a wind pressure. Wind pressure is required to be considered while consider only on that portion of the dam structure which is exposed to action of the wind. Normally, wind pressure is taken 1 and 1.5 kN per meter square for the area exposed to the wind pressure. So, value of the wind pressure is we consider 1 to 1.5 kN per meter square. Wind pressure is not a significant force and therefore sometimes not considered in design of the dam. It is the earthquake forces. If dam is located on seismic regions, it should be designed for earthquake seismic forces, and earthquake uh, produces seismic waves, which is capable of shaking a foundation upon which the dam is built. The effect of earthquake is therefore equivalent to imparting the accelerations to the foundation of the dam in the direction in which the wave is traveling at the moment. Earthquake waves may move in any direction, and for design purposes, it has to be resolved in vertically and horizontally components. Hence, two accelerations, one horizontal acceleration and one vertical accelerations, are induced by an earthquake. So go through more about earthquake forces and seismic forces in this topic. Okay, and so these are the uh, forces that acted upon a single gravity dam. Okay, thank you.